All right, so we're going to start. We have 4 problems. These should go actually pretty quickly, considering some of them, these aren't as lengthy, but they hit really good ideas, okay? So first one, it says 3 pure solid compounds labeled X, Y, Z are placed on a lab bench where the objective of identifying each one. It is known that the compounds listed in random order are KCl, Na2CO3, and MgSO4. So you might want to highlight those or rewrite them somewhere, because that's what this is all about. A student performs several tests on the compounds. The results are summarized in the table below. Okay, so here's the goal. I'm going to write these down so we can try to place them. Okay, so we have to figure out which one is which. So when you just look at this X, Y, and Z, let's take a look at what the graph or the table tells us. It says pH of an aqueous solution, meaning I throw these into water and it dissolves. Note, greater than 7, 7, 7. By adding NaOH. So I add a base to these, no observation, and precipitate. I add an acid to this, a gas, no observation, no observation. So what they've done is they clearly have shown there's a specific difference, but there's not a lot of other differences from each, right? There's literally one difference from each one. So there's no right or wrong answer to start on each of these, but basically what you're doing is this one, the first column with the pH, that's our knowledge of if you drop it into water, is it basic, acidic, or neutral, okay? Second one, does it make a precipitate, or are both things aqueous? And then the last one, does that, by adding HCl, make a gas as one of the products? So I'm actually going to try to go in order, at least do this first one, pH. What did we learn? Which one creates, remember the trick, you add an H plus and an OH minus. If one makes a strong, they both make strongs, it's neutral. So two of these must make 2 quote unquote strong acids and bases if you combine the H and the OH. But one of them must make a strong base and then in theory, remember this is a trick, a weak acid. So which one is X? Katie? Na2CO3, because if I put NaOH, that's a strong base, and HCO3 or H2CO3, or however you want to think about that, would be weak acid. I'm already thinking of the next thing. So, yeah, that should be definitely that one. Now, let's just confirm that, because it says it makes a gas. What gas would that make? What gas is that? So if you add H plus to this, what it does is an acid obliterates this thing. It severs it apart. So what gas would be produced, do you think? CO2. Technically what is made is carbonic acid, but then what have we kind of learned? Carbonic acid immediately breaks up into water and carbon dioxide. Okay, and you may not have those steps down, but you should be able to kind of recognize, well, that's carbon dioxide. I don't really see another gas in here. Okay? No, it will become carbon dioxide because the other O goes to water. Okay, so now we got to go to here. So I guess the only thing I can go off of, honestly, is this, right? I mean, there's nothing else. Or you could say no observation is observed. So observation is observed. No reaction is observed, meaning that there's no precipitate. So which one makes a precipitate? So what I basically have to do is I'm going to add NaOH to both of these. So it's a double replacement reaction. Any precipitate is a double replacement reaction in our world right now. So which one is the best bet on making a precipitate? And you should be able to actually do this pretty quickly. Kevin?
The Mg.
Yeah. And the reason why you should be kind of confident on that is that, remember, alkali metals automatically won't, right? And this one's the other alkali metal. So aren't the alkali metals just switching places? So if alkali metals are being the cation, then it will automatically be soluble. So no precipitate. Okay? So you get 2 points. 1 point is earned if you get one of them right. You got 2 points if you get all 3. Listen to this, because I get some people are crafty. No points are earned if all 3 are the same compound. And no second point is earned if 2 of them are the same. So you can be like, Na2CO3, KCl, KCl. You don't get the other point, which I think is really smart from the test taker's grader's point of view, because they could see, well, then you're just bailing out and you're trying to get one of them. So, I mean, the whole thing's only worth 2 in the first place. So you have to commit. So basically, you got to get all 3 right to get 2 right. I don't know how you could get 2 right and still write all 3. That would be very crafty on your part. All right, so there you go. Moving on, letter B. Write the chemical formula for the precipitate produced when 1 molar NaOH is added to the solution. So, right here. So letter Z, what is the precipitate? Please write it out. What is that? The formula is what it's asking for if you don't quite understand what it means. It does say chemical formula. What is the chemical formula of a precipitate that is from the thing I circled? Formula white precipitate. Steve, what do you think?
NaOH plus MgSO4 equals MgOH plus NaSO4.
So you just need the precipitate. And you wrote that. It's very close. It's very close.
OH2.
With a parenthesis. If you don't put the parenthesis, it's wrong. Right? Because it's 2 OHs. So it did not say the whole formula, so just make sure that if you did write a whole formula, as long as you wrote a solid or a down arrow next to the one that is the precipitate, you would get credit for those points. All right, moving on. C, that's 1 point. Explain why an aqueous solution of compound X has a pH value greater than 7. Write an equation as part of your explanation. Okay, you cannot use the trick that I teach you. Can't say I add H plus and OH minus, and what it did was made a strong and a weak. It's not actually the real, that's not what's occurring. So here's my suggestion to you. Write the equation first and then explain it in terms of the equation. What do I mean? This is how you should start it. What has to be present on the right side, H3O plus or OH minus? OH minus. So here is what you have to think about. What's happening with the water? Losing an H. Right? So the H has to glom on to which ion? It has to be this one. And you have to do the ion. These are salts. They break up. So what does it make? Technically, we're not writing carbonic, although I think you could get away with it. But it'll be a form of that. If you did write it like that, you still, it doesn't change this idea. Okay? So, just to be totally upfront, you usually, and when we first learned this, I did bring this up, but I knew it was going to confuse everybody. You always use the ion that is the opposite of what helps us figure out the actual pH of it, or range. So it'll always be the opposite one that will create that because of just, I always like the water. Write the water first. Okay, what happens to the water? Makes an OH, makes an H3O plus, and then I can dictate which ion that has to glom onto or to be taken away from. Okay. Explain why then? Well, what you can just say is simply this. How do I always explain pHs and why it's basic or acidic? Because it produces OH minus. It produces H plus. So what you could say is the CO3 2 minus in water produces OH minus. Done. You don't need to go in as a depth as you may think because you are getting to the heart of what it is. Every time we write about pH or every time we talk about pH, if you're relating something being acidic or basic, you have to have an OH or an H plus sitting on the right side, on the right as a product. So all you have to say is that this creates the OH minus. The CO3 2 minus will create OH minus in water. And that's your explanation. And you get 2 points. 1 point is earned for identifying. You could say that this is a base. This will act as a base because it gains an H. You could say that as well. And then 1 point is earned for a correct equation. All right, D. One of the testing solutions used was 1 molar NaOH. Describe the steps for preparing 100 mils of 1.0 molar NaOH from a stock solution of 3 molar NaOH using a 50 ml burette, a 100 ml volumetric flask, distilled water, and a small dropper. Oh, Larry, we have talked about this literally this morning. Okay, so what do you actually need to know first? In general, there's something else you need to know.
How much?
How many milliliters of stock solution you need? You would need to do that. It's kind of a hidden step. So you would need to actually start with that first. So just looking at the values here. Right? So I'm going to need 33 mils of the 3 molar. Okay? So, I'm going to try to summarize this. In general, what do you need first? It says using a burette. So you probably use the burette to deliver or to drop or something 33 mils of 3 molar NaOH. You could have said you put water in there first. Then what do? It's in the volumetric now. What are we going to do? So I have 3 molar, 33 mils in the volumetric. I'm going to add water where? Or to what?
The line.
Just below the line, right?
Just below the line.
Add, and I'm reading what it says. It says distilled water in the list, so use those phrases. Add distilled water just below the line. I might be cutting off a word here or there. And then how do you finish it off? It told you to add a small dropper. Using a small dropper, I'm going to be really technical here. Although I'm not being technical, I'm just calling it a line, calibration line. I did look that up. So using dropper, add H2O until bottom of the line. Meniscus is there. Then, technically, I don't know how many steps I'm supposed to do. What do we need to do to finish this off? Cap and invert. Cap and invert. Cap and invert to mix. Why I say to mix is then that means I'm probably doing it many times. This is way dated, but my professor always told me if I sing the Gilligan's Island song, then it would be done. But it's probably like a happy birthday, same kind of thing, or the alphabet. It's about as long as it would technically take if you wanted to really mix them, you know. We literally had to one time sing. Everybody had to sing Gilligan's Island, and some of us didn't know all the words.
Were you one of them?
I don't actually remember. I think I knew most of them, or maybe I acted like I didn't because I felt like I shouldn't. I'd like the show a lot when I was a kid. Describe a simple laboratory test that you could use to distinguish between. Okay, these are really good questions for us to go over because it's not as complicated as it sounds. Between those two, in your description, specify how the results of the test would enable you to determine which compound is which. Listen to this really carefully. You don't need to be able to say both. If you tested it and knew what you were looking for in one, automatically, I hope this makes sense, automatically you would know the other one. Right? So if you're testing A and B and you know that A is going to do something, or the identity of A would do something, and all of a sudden there it is, automatically you know what B would be. So what's something we could do? What's things in labs that we can do to find an identity? These aren't that complicated. You've done them. You could do a single. I didn't even think about a single. That's interesting. You could do a single replacement reaction. Then you'd have to know. You have to come up with a metal though, and the hard part is you may not have that info. That's not a bad thought. That would work. You'd have to have one in between these two then, though, right? And actually, I don't know how far apart they are, so you have to actually find the metal. Of course, they're right next to each other. So that won't work. It's a good idea.
Could you add something with SO4 and then if this, like the CA will create precipitate with the SO4?
So you can do a double replacement reaction. So you're looking for CaSO4, which you know is a precipitate.
Yeah.
That's not a bad idea either. Let's even make it simpler. What about solubility in water?
One will make it acid.
No, not even that complicated. Just solubility rules. So you talked about precipitate. You're on the right track. This is slightly soluble. Why do I know this isn't? Alkaline metal. Right? Automatically very soluble. What if I drop both these in water? Which one's going to dissolve? This one? Right? This is soluble. So you could do solubility. Kevin, not a bad idea. The only thing I get worried about sometimes is like, what if you don't have... It depends on what they supply for you, and they didn't. This is very vague, so yeah, you could definitely come up with something. You have to get specific though, so you have to say something. what I would do, by the way, is you'd have to have probably some alkaline metal in there.
Right, so could you do like Li2SO3 or SO4? Because then everything would
Yes.
create
Yeah.
everything would be soluble.
Yeah, that's a good point. Yeah, because then the Li would make sure that the Ca. Yeah, you could do that, something like that. Definitely, that's a good idea.
If you add like HSO4.
Acid,
Yeah.
you could do H2SO4. Only problem is that sometimes it breaks it apart, and now we're actually looking at gases and not precipitates anymore. You want to do salt with salt. So good idea though. Here's the other one, and I want to say out loud, and we did this, and I need you to know. They don't stress this nearly as much anymore. You used to literally have to memorize every flame color. It's not bad to look at it. Look at your blue sheet. It's not bad to look. If it randomly comes up, those are those ones that just, hey, we're trying to differentiate between one score and another in a multiple choice. But there's one you should know, for sure. Sodium in a flame is a yellowish orange. I always think it's a bright yellow, but then some people say orange. If I can spell it. Good luck, guys. I'll be out there as soon as I can. Be aggressive. So, sodium, you got to know that that's a yellowish orange. That's the most common, the most used as a flame test. Now, you wouldn't need to know that one. It's a brick red. If you want to know, it's an orangish red. But sodium, yellowish orange, like that's usually in a problem. So if I just put them both in a flame, the one that makes it yellow is that. That's actually why, like, if you put a glass stirring rod or any kind of glass into a flame, it turns yellow, is because the sodium inside the glass is actually reacting. So either one, you get 1 point earned for any reasonable test. So some of those I wasn't dissing. It's just, unfortunately, some of them you'd have to really be specific, and then that's great. And then 1 point is earned for interpreting the results with the identifying one compound. So that is that problem. All right. Next problem. We're dealing with some gases here. So, is this the right order? Is that the next one? Maybe like a formula? Yeah, good. All right. A 8.55 mole sample of methanol is placed in 15-liter evacuated rigid tank. Again, what that means is just empty, and it's rigid, meaning the volume doesn't change. And heated at 327. At that temperature, all the methanol is vaporized, and some of the methanol decomposes to form carbon monoxide gas and hydrogen gas. It says some. You might even want to circle that. Some, as represented in the equation below. Yes, Rory.
You got H2O, and on here it says just H2.
Right.
All right?
You're right. You're right.
Okay. Too much.
Better?
Yeah.
I see it. It's not gonna bother me. The reaction mixture contains 6.3 moles of CO at equilibrium. I calculate the number of moles of H2. So I want moles of H2. What it told me is that I have 6.3 moles, 6.30 moles of that. Well, if I have moles of CO and I want moles of H2, this is just story. This is just a conversion. So I have 6.3 moles of CO. For every 1 mole of CO, it looks like I have 2 moles of H2. And there I go. 1 point. Some of these you don't have to overthink. It does not mean that the last letter on a problem is the most difficult, but usually the first problem in an entire passage is usually not the most difficult either. So it doesn't mean it gets harder, but usually they don't come out all gangbusters right away. Calculate the number of grams of CH3O remaining in the tank. Okay, this is important, and most people have probably misinterpreted this when they did this test. This is the amount that was actually made. So I have to use that to figure out how much exists at the moment. How much was like left over from that reacted, I guess I should say, because it's asking what is remaining. So if that makes sense, like if that much many moles of CO was produced, how much of that created, how much of this created the CO? Okay, so it's a 1-to-1. but if you have to show your work, just want to officially show this, you could come up with some other ways, or say a 1-to-1 ratio or something like that. But yeah, I could say reactive case. You got to come up with some sort of extra label just for you to have that idea. So I know it asked for grams, but in the beginning, how many moles actually are remaining? What do I do? Rory, what?
8.55 minus.
Yeah. So what started, this was the initial amount, and that was the key thing in the problem. It said some reacted. So that's how much we started with. This is how much we left or ended up with. Right? So it's initial basically minus the ending, or what was reacted, or however you want to think about it. Does that answer my question? It's asked for grams. Always go back. When you are done, just double check. It is such a shame if you just did not execute a problem. Oh my gosh, it was supposed to be in joules. Oh my gosh, it was supposed to be in grams. I could have done that. So, I need to convert this. Always show work. You should have plenty of time. Molar mass is 32 approximately. And you get that, so maybe doubled and then some. So 72 grams. I know it's easy when it's like, oh yeah, I worked you through it all, and there you go. That's why, we gotta, hopefully we've been working on those other problems too, and we'll come up with a few more on some of our reviews coming up yet as well, that give you a couple opportunities to get to calculate something like that without me giving it to you first. That's all. Unfortunately, I would have totally guessed that was worth 2 points. It's only worth 1. It's also always nice to see. Oh my gosh, I didn't quite get that one. It's only worth 1. Every point though really matters, so we fight for everyone. Calculate the mole fraction. All right, they've been doing this on purpose. They're giving us moles. What's a mole fraction? It's the part of the mole that you want over all the moles. So I want mole fraction of H2, so that's in green. So I have 12.60 moles of H2, and I'm going to label that just so I understand I did that one. And now what do I need? I need all the other moles. So I have 2.25. That's from the H3OH. And try to go ahead of me if you can. I'll give you a second. What else are you writing in there? Again, a mole fraction does not have a unit. It's just a fraction. Hence the name. What is the mole fraction?
Can you give it a mole decimal?
Yeah, it'll be a decimal. Yep. Don't forget the one you put on top. Big common mistake. Like, you got to divide the same number that you used. When you're done, you can look up. Believe it or not, that's 2 points. I would have totally given 2 points on the last problem and 1 point on this one, honestly. Well, what if I did something wrong? If you're using the numbers correctly from above, you should be able to get credit for this. At least in theory, you should. This is something I don't understand. And then lastly, calculate the total pressure in ATM in the tank. Okay, total pressure. They're trying to go out of their way for that. So if I want total pressure, there's 2 things that you have to be aware of. The pressure that's total can add up. You can have multiple pressures. What's the other thing that can add up? Moles. You're not going to add up temperatures. This one's at 100. That one is too. My God, it's at 300 K. Like, no, it was at 100. Whatever it is. So, I'm writing it like this one's just to really emphasize that. Volumes don't add up. Anything else? So, what's my N? like 21.15 or whatever. And then I include everything else. Where do I get that? All from the beginning. We strive for 3 sig figs. The problem gave us more or less 3 sig figs throughout. There's 327 Celsius. It says it in the problem, that's 600 K. We're doing great on time. We're only 1/3 of the way through, yet we're almost halfway done. B. Consider the 3 gases in the tank at 327. There are the 3. Okay, this is more conceptual now. And either you get it right or you don't. Like either you know these or you don't know them. So it's important to really process this. Highlight, circle, when you're going back through some stuff. This was big on one of our chapter tests, I think on chapter 7. Or chapter 5. Chapter 5. How do the average kinetic energies of the molecules of the gases compare? So how do the average kinetic energies compare?
Are they not all the same because it's at the same temperature?
Exactly right. Kinetic energy is based on temperature. If you're unsure, anybody, do you have your yellow sheets? I want to show an equation. Sorry.
I should have said
You botched that bad. I mean, that was horrible. All right, they don't give me this equation anymore. There used to be this thing, kinetic energy equals R, something with RT, and it was like, well, there's a temperature, so it's all dependent on temperature. So it's the same temp. So because it's at the same temp, I want to answer correctly. How do they compare? They're going to have the same kinetic energy. Right? Kinetic energy is based on temperature. Based on temperature. It's based on motion. Temperature affects the motion. But, because, well, yeah, we'll leave it right there. Which gas has the highest average molecular speed? Speed is not energy. Okay, so, there are many ways you can look at this. There's gas, Graham's law of effusion. There's also this. And what's that contingent on? And don't, this is more on speed. I know that's confusing because it says KE for kinetic energy, but this is the motion, how fast it's going. Velocity.
Like when you have like root mean square, like the speed for that stuff. Isn't that what that is?
Yep, that could be it.
Okay. Like.
Yep.
Isn't like the smallest mass the fastest one?
Yep, sorry, I was with infusion. Effusion, we did the molar mass of the other molar mass, and then you do square root, same idea. Exactly, it's based on mass. So, which one, it says which gas has the highest average molecular speed? H2. It would be H2 because it has the lowest mass. Try to not say lighter weight. Physics, lighter is, you'll get away with it, but it's not. If you can say anything with mass, it's better. Although this is not physics, weight is about gravity and mass together, because there's a force involved. So, the less you can talk about mass or weight, the better. Both those are 1 point. Hopefully you kind of predict that. Finally, the tank is cooled to 25 degrees, so very cold compared to what it was, which is well below the boiling point of methanol. If it is found that small amounts of H2 and CO have dissolved in the liquid CH3OH, which of the 2 gases would you expect to be more soluble in methanol? Okay, you don't understand what it's saying? Draw a picture. So basically, what you have is you have this liquid methanol, and what they found is that H2 and CO are in there. Which one would dissolve more? So what have we talked about with solubility? You have to talk about both, and you have to talk about its interactions between them. That's what you have to go with. So which one would be expected to be more dissolved or more soluble? Well, let's talk about this first. Okay, so what do you have? You have a little bit kind of the LD side, right? And then mostly H bonding. Okay. So the solvent that you're talking about has some attractive forces. So of the two, which one's going to interact more effectively? CO. And you would have to probably, I would try to state something. I would say that H2 has LDs and it's nonpolar. Where this has a slight I thought it was a car. There's a small dipole. Well, you're like, wait, dipole and hydrogen bonding are different. Hydrogen bonding is just a super, oops. It's just a super dipole. It's just a really strong dipole. So the interaction would be greater between CO and COHO3 because of the more similar IMFs in the interaction. Again, you got to surround. The solvent molecules have to surround the solute. You have to have interaction. If they don't surround, what they'll do is be more attracted to themselves, either the solvent or the solute. So what happens here with the H2 is that the solvent molecules will just like walk right by it and just be more attracted to themselves. And then the H2 just passes by. Same idea if you put something really polar in a non-polar solution. Oh wait, why won't that work? Because the ions that were really polar would just be attracted to themselves again because they're not getting surrounded by the solvent, so it wouldn't dissolve because they're not going to be surrounded. And that's that. It's 1 point again. All right, let's go to the next one. Little atomic structure for you. I'm going to let you do this first one. Answer the following questions refer to or related to sulfur and one of its compounds. Consider two chemical species, S and S2 minus. I. Write the electron configuration of both. So you could write it like that. What do they look like? What is the electron configuration? So you'd have a periodic table on the test. What do those look like? 1 point for each, by the way. This is 2 points. Are you saying an answer or asking a question?
That's a good question. Are both considered to have the same like nuclear charge because of the same amount of protons?
If you have a different number of protons, what happens to that?
Well, the size is going to change.
Size will change, but let's just make this up. It's number 16. What if all of a sudden it had 15 protons? You know what happens to sulfur? Anybody? What do you ask? If you have sulfur, Kevin's asking what changes does it still? He's asking, do I assume it still has the same number of protons? What if it all of a sudden had 15 protons? What happens to sulfur?
Phosphorus.
It's now phosphorus. Oh, you mean like hypothetically? No, it actually is now
So
phosphorus.
protons.
Protons are the identity of the atom. So when you write two of these, then it always has the same protons.
Yes, that's what I'm saying. So they not have the same amount of protons? Like these two right here.
So they will have the same protons because I wrote the letter S.
No, them are electrons. The 2 minus?
I'm saying S and S2 minus, they have the same amount of protons.
Yes.
They will have
Okay,
the
yeah,
same-
that's what, that was.
No, I know, and that's what I'm explaining.
Okay, yeah,
Yep.
that makes sense.
Okay. Yeah. So electrons and neutrons can always change. You change protons, you change the identity, and that's what alchemists have been trying to do for years. Is try to make gold out of junk. And you can definitely make some gold. Problem is the amount of money you spend doing it, and either removing or adding protons, you're actually in the hole. So
Is somebody in Shark Tank?
that is Mark Cuban.
No, no.
Rory, what is the first answer?
1s2, 2s2, 2p6, 3s2, 3p4.
Justin, what's the difference on this one?
That last one's 3p2,
Close.
3p6.
Yeah. It's negative. You have two more electrons. Electrons are negative, so it's 3p6, and then everything else is the same. I just want to ask, they didn't say this, but they are allowing this. If I wanted to do a noble gas configuration, anybody, we'll just do this one, just nice review. what would that look like?
And
Ne, then
3s.
3p4, and the other one would be 3p6. Okay, because it's always the last energy level, or the last row. By the way, that, let's just say it was selenium instead. It'd be argon, and then 4s2, 3d10, 4p4. It's everything on that row. Everything on that row.
So you can't just do like AR for
No.
S2-?
Good. No. It's always cheating, yes. And everybody always tries to do that. It's a good question. Or even for AR itself. You can't do AR, right? Because you got to have something. You always got to go to the previous one. They're very strict with that rule. All right. Look at totally sick.
AR-15
It'll be like guillotine.
instead of AR-18. Yeah.
I'm not judging. I'm trying to relate.
I play it during tennis play.
Relatable.
Walk up.
Explain why the radius of the S2 minus ion is larger than the radius of the S atom. So what they're basically saying is this. I'm just making this up. I don't know the actual sizes. But that's what they're saying. Just good visual. So, can I use nuclear charge? I can, but not as my overall conversation. I could. I still can. But it's just a little different. There's a better argument. Because there's still 16 protons. You got to talk about the differences. Always talk about the differences. So this one has 18 versus this has 16. So,
You mean the electrons?
The way you said it was so sensitive.
and I'm assuming what you're really referring to is that, obviously. Yes, thank you, Lori. So, what could you talk about? You could talk about how each electron here has a weakened pull. Would that make sense? Like each of these has only 16 protons pulling on 18 electrons. So the nuclear charge, the effect on the nuclear charge is weakened, so each electron is able to get further away. Here's another one that we haven't really talked about much ever, just giving you other ammo to do, is that you could say there is more electron to electron repulsion, because, by the way, they're all next to each other. There's a lot of repulsion, so they're pushing away each other. The only reason why they don't get further away is that the protons pull them back in. So if you have greater electrons, you're going to have more repulsion, and they can get further away. But I actually, if I was doing the test on this problem, I would have talked about how it's like a 1-to-1 ratio, and the electrons are experience a certain pull from the nucleus, while each electron is receiving a little less of that pull because there's a greater number of electrons than protons. So the electron cloud is able to get further away.
So you can't just say more electrons basically.
I don't think so.
Right.
I don't think so.
Keep it simple.
As you notice, though, I like these problems where they state what the answer is already, then you have to come up with an explanation. I think those are really effective, because you don't have to come up, you have to just make reasoning out of it. You could run into a problem that you don't understand, and you could potentially get from A to B to C because they've already told you the answer. So, triple I, which of these two species would be attracted in a magnetic field? This we have done just months and months. We've done this one. So the instinct always is S2 minus. Why? Charge. It's not the case. So please, if you're lining these up, I'm just going to line them up. Well, I'll do this. I'll do S and S2 minus. Check this out. This usually comes up every year, and you just got to remember this. We have gone over this. The one that is attracted in a magnetic field would be the sulfur. Why? Because you have unpaired electrons. Okay, you have unpaired electrons.
What if they compare two that are like
This,
both unpaired?
they won't. They won't do that. This creates a net magnetic, I don't know what they would say, moment, I guess, or a net, an overall a magnetic attraction that could be then attracted in a magnetic field. It has a magnetic property to it, or a magnetic attraction. The reason why they ask a question like this is that they are suckering people into going, oh, magnetic, poles, charge. Poles and charge. You know, charges have partial charges on each side, and we sometimes say there's a positive and a negative end, and then people say there's poles because there's polarity. I get that. It's not the same idea. So just know, unpaired electrons. There's other questions like which one would be more attracted in a magnetic field? Well, the ones that have more unpaired. So like nitrogen would be more attracted because it's one less, or phosphorus, or nitrogen, because I'd have 3 unpaired electrons, as an example. So that would be my answer. That's more attractive in a magnetic field. Unpaired electrons. That's the key. B. Here's another term that you can get away with, usually isoelectronic. If you don't remember what that is, they usually tell you what's happening. So you have S2 minus, and you have argon. And it says S2 minus is an isoelectronic with AR atom. From which species? S2 minus or AR is easier to remove an electron. To be honest, isoelectronic, if you didn't know the word, you can still get this right. Does anybody know what isoelectronic means? Just looking at these two.
It means their electron charge is same.
Not electron charge is the same, you're really close.
Just the amount of them.
The amount of electrons, right? Different protons, same number of electrons. So what it is, it's usually all of them that look the same ions. So for example, all of these and then K and Ca, all when they become an ion will look like Ar. And then all of NO and F and Na, Mg, Al, they lose, they gain, they all look like neon. Those are all isoelectronic. So I'm just going to write this down. I have 16 protons, 18 electrons. Here I have 18 protons, 18 electrons. So again, isoelectronic, that's what that's referring to. But you didn't need to know that. It says, which is easier to remove an electron? And explain why. Which one is easier?
S2 minus.
Why? It says, explain why.
There is more, or there's less protons, there's less pull on the same amount of electrons.
Perfect, done.
Oh,
If you want to drop a good word, you could say that S2 minus has a lower nuclear charge, right? Which does not hold the electrons as, what word am I looking for? Tightly, maybe, or something like that. So you could drop nuclear charge in there as well, like a guillotine. I'm getting closer.
Good to know. You know that old.
Don't be thinking of
I'll get Mr. Smarov in here. In the H2, okay, this question has come up in the past as well. In the H2S, the HSH bond is close to 90 degrees. So they're literally saying this, or this is about 90 degrees, roughly. On the basis of this information, which atomic orbitals of the S atom are involved in bonding with the H atoms? Okay, you know this if you don't. And by the way, it's only 1 point if you don't. What would this normally be? If I asked for the angle and you didn't know anything else, what would you actually say that would be?
105.
105. It should, I'm just going to put it way over here. It should be 105, but it's not. Whenever we talk about those angles, 105, 107, 109.5, those are all hybridized, meaning that comes from an sp3, correct? 1, 2, 3, 4. It came from an sp3. So if this ever comes up and they say an angle that doesn't make sense, then it has to come from something that's not hybridized. So what things create exactly 90-degree angles? What orbitals? Do you remember? This is way back now.
SP3
Way too many things. No, it's not hybridized at all. I'm looking for one letter.
S.
So S's are a sphere. So I really can't make a 90-degree angle. Is there only one of them?
D.
These are crazy. I'm not going to draw it. It's the P. The reason why is that they are vertical or they are horizontal. So right there, there's my 90 degrees. So it must be from the P orbital, specifically the 3p orbital. It must be a 3p or a p. You could say just p. Because they make vertical and horizontal, they're in the vertical and horizontal planes. You're going to have to trust me if you're like, I don't remember this at all. It was like literally there was a question in one of our packets and it had this exact same problem, to be honest with you. And then we went over it one other time, but it's a long time ago. It's kind of a trick question. But that's the result. So I guess to me, if the angle doesn't make sense, you got to understand all the angles we've learned are always hybridized. So can you just go back and be like, okay, well then it must just be, it's usually the question, the answer is usually P if it's not, because those are the ones that make like double bonds, the pi orbitals. There's sigma and then there's pi. The pi reach up and over. I know what I'm doing. finishing it up. Two types of intermolecular forces present in liquid H2S are, so, okay, talk about this. They're saying there's London and there's dipole-dipole. They're telling me this. I. Compare the strength of the London of the H2S versus the H2O. If I'm reading that right. Yep.
Can I answer?
Oh, you can answer in 1 second. What am I always doing when I'm comparing? I look for the differences and the similarities. So in this case, I hope that you recognize, well, I'm attacking the S and the O. Okay? So, how do I compare Londons? Kevin, maybe I'm changing your answer, but
Well, as I say, wouldn't the London forces be stronger in H2S because they'd be weaker in the H2O because of the H bonding? I don't know.
I hear what you're saying.
Do you
No.
have to relate to H bonding?
no, act like you don't even know about it, because you're not actually ever going to talk about
I
it.
don't even know about that.
Isn't there?
What's the difference between one London to the next? What makes one stronger, one weaker?
Size.
Size.
Shoot.
So, oh great.
How is there London forces in this?
Don't worry. Everything has London.
Okay.
Think of it this way. Remember, the larger the atom, it's all about electrons being temporarily imbalanced, which causes an induced dipole because all the negatives are on one side and all of a sudden the next electrons go whoops, whoops, and they all shift. So, which ones are stronger? The larger electron clouds, right, they're the same group. They did this on purpose too. They're in the same group. So there's one more energy level. So S is larger, so it has a larger LD.
Isn't like F the strongest one?
That's something different. That's electronegativity. That's pulling electrons. That's different.
Think of the snowman with the size.
Gotcha.
Compare the strength of the dipole-dipole. So, this is where electronegativity comes into play. You have the differences HS to O, H to S and H to O. This bond dipole is much stronger than that bond dipole. And in fact, this is an H bond, which means that it's a much stronger dipole. And the reason, if you don't remember, the reason why is because there's a greater difference between the H and those three elements. There's a greater difference in electronegativity of F, O, and N than the other one, so it creates a greater dipole. So the stronger dipole should be that, and if you want to go on the H bonding and say H bonding are the strongest of the dipoles, that's great. Or you could say that the dipole moment is the stronger between the two because the electronegativity is greater, the difference is greater between OH than it is between SH. If you want to even go further, you could state that O has a greater electronegativity than S. I will read what they have just so you understand in a different, more thought-out answer. The strength of the dipole-dipole forces in liquid H2S is weaker than that of the dipole-dipole forces in liquid H2O. The net dipole moment of the H2S molecule is less than that of the H2O molecule. This results from the lesser polarity of the HS bond compared with that of the HO bond. In parentheses, S is less electronegative than O. One left. We're doing great. All right, little kinetics. Always good to do a little kinetics. So I'm going to let you guys actually right now answer both A and B without me. I'm going to pause the video so it jumps right away. So if you're watching at home, please pause and work on A and B. Determine the order with respect to H2 and with respect to Cl2. All right, so what's the order? Katie, give me the first one. A, what is that? First order? Yep. I'm assuming you did the same thing I did here. Is that you want to find the difference between the one you're looking at and these should stay the same, right? So definitely I could do this with the math. So this over this concentration equals 2. You take the rates, and you could have just said the concentration doubled and so did the rate. Well, just so you understand how that works, is 2 to the blank, 2 to the x equals that. That's how that always has to work. It's not the rate to the whatever. It's the concentration to the rate. How does the concentration change affect the rates change? Okay. Erica, what'd you get for the second one? Yeah, it's also first order. And it's the same exact concept, right? This time, you are using these two, so these stay the same. That doubled, and so did the rate. Right, so it would be similar math. They did not use math. They just said the order of the reaction with respect to H2 is 1. Comparing experiments 1 and 2, doubling the initial concentrations while keeping the initial concentration of CO2 constant results in doubling of the rate reaction. So just understand there wasn't anything more that needed to be said. You do need to say something, so the math would do it for you. If you feel comfortable doing that, I'll tell you I would have done the math. Looking back on here, I'm looking at this. I know I could do this without the math, but that makes me feel safer. But you could just say doubling the concentration, and you could even say in experiments 2 and 1, doubling the concentration doubled the rate. That's the first order. You could say it like that.
How would it be second order? Like, what would you say? Like doubling the rate?
This would have to be a 2, and this would have to be a what for second order? This would have to be a 4. So by doubling the concentration, the rate quadrupled.
So then if it was like, if that was the first one, the left side was 3, would that, the other
That's
one
0
would
order
be-
then. If this is 3 and that's 1,
No, 3 and then 9.
yeah, that's second order still.
And then would that one be quadruple?
Say triple and multiplied by factor.
Yeah, then you're gonna have to start showing math, or just say, yeah, as the concentration tripled, the rate increased by 9 times.
Okay.
You can say it that way. I don't actually know the term for that.
Yeah, I don't either.
I'm sure there is one. You make them have to look something up. You're like, no, I don't know this term. Yeah, I got that too. Wait, it's all from Pulaski. Nah. Everyone's using the same exact phrase. Write the overall rate law. I hope you have this. People forget how this works. Okay, let's stay here. Rate equals K. You gotta write rate. You gotta have a K. People forget what this looks like. And then you have to have H2, your reactants only. If it was a second order, I'm going to do this in red for a second. If that was a second order, you put a 2 there. If it was a 0 order, you could put a 0, or you could get rid of it. Either one works. If you feel more comfortable writing 1s there, that is okay. It's just, if there's nothing there, it is a 1. So that's that. D, write the units for the rate constant. Okay. If you forget this, like when you're in the middle of this, usually you do really well on this. But if you forget this, the rates are right there. It's molarity over time. So I could do this. I'm going to plug this right underneath. I'm just showing you how you could figure this out right now. You're looking for K, and then what is this? It's molarity times molarity. Right? I mean, that's how you could figure this out. So then what do I need? I need this side to equal that. Right? So what do I need to do? I need to get rid of one of those, right? So I need to invert that, and it's liters over moles, and then I need my time. Why? Because I don't have time on the right side. What I always just remember is this. Let's just call it n minus 1. It's 1 less than the order. So if it's 5th order, it'd be liters to the 4th over moles to the 4th times the time. If it's 1st order, these become 0, so it's just inverse time. It will always come up on a kinetics problem. It will always ask a unit of a rate constant, always. So it's worth your time to focus on that and look at a few extra examples.
For the n-1, is that for the overall?
Yeah, overall order, right. Yeah, so yep, good. So this overall order is 2. So that means that I should have a 1, right? These should be 1s then, right? Yeah, overall order, yes. Okay. doing well. E. Great question. Predict the initial rate of the reaction if the initial concentrations of H2 is 0.003 molar and Cl2 is 0.00500 molar. And that's all it says. You can't plug this into letter C because you don't have a K. If you had a K, you could plug those in right now, get my rate. But you don't have a K. So there's a couple things you could do. This is not how they do this. Could you find K? You could plug these in, plug that in, get K, plug it into K, and then reestablish. You could do that. They don't. But that is definitely a great step. Usually what they do is they will prompt you to find a K. So there's got to be another way that you won't have to do extra calculations. So talk to me about each one, just looking at rate, or one in the table. Like any differences or similarities, and what's happened to them, so we can compare it. Kevin.
CL stays the same.
Okay, so CL2 is exactly the same. So if it's just about CL2, the rate should be the same as it was in the, let's say, is it experiment 1 or trial 1?
Yeah.
Okay, what about the H2? Tripled. Okay, so what order is H2? First order. So what does that mean? Whatever happens to the concentration, that's what happens to the rate. If I double the concentration, I double the rate. If I triple the concentration, I would triple the rate. That's the definition of first order. So what would happen to the rate constant? Triple. By the way, what if you tripled both of these? What would happen to the rate?
9.
Well, this one would cause it the triple, and the other one would cause it the triple as well.
6.
Is that?
So 9.
Isn't that 9?
That is definitely.
It's not 27. So you could triple the rate. I like the other idea of plugging it all in, getting your K, and then replugging it in. But it would basically mean, because it's first order, this would triple the rate. So what is the rate? 1.82, so it becomes what, 5.46 times 10 to the negative 12th. And then you need a unit. I think it asks for that. No, it doesn't, but the unit's from the table. So I just took 1.82 times 10 to the negative 12th and I multiplied it by 3.
Could you use that integrated rate law? Or do
No.
you need to take
Integrated rate law is only about time. If it doesn't talk about time, don't do integrated rate laws.
Are they gonna be
And if you do an integrated rate, no, you won't have to graph one, ever. We did that because that's chemistry and I think you should learn that, but they won't make you do it because they're not making everybody have a graphing calculator.
Do we need to do the integrated rate law at all? Or like, is that on their
Would that
yellow
be a
sheet?
problem, do you think?
Like, is that on the yellow sheet?
The yellow sheet has first and second order
Okay.
integrated rate laws, the y equals mx plus b format, yeah. You might need those, which we did one the other day, but we'll try to, I think we have a couple in our review sessions this weekend. All right, last 3 problems and we are out. The gas phase decomposition of nitrous oxide has the following 2-step mechanism. So, step 1. Step 2. F. Write the balance equation for the overall reaction. Doesn't say anything else. Well, if these are steps,
No way.
you set them up. So, looks like that cancels. These add up, so it's 2N2O, 2N2 plus oxygen. To point. Take it. Please take it. Only reason why they make that easy is that they're setting you up for a final problem. G. Is the oxygen atom a catalyst for the reaction, or is it an intermediate? Explain. The explanation, all it has to be is it was introduced, then consumed, or it was produced, then consumed. That's all you have to say by stating that. So, Suku, what do you think? Is oxygen, wait, and I want to make the oxygen atom, not the oxygen molecule.
Wouldn't be an
Because?
It's produced,
And then consumed.
or yes.
It's important because if you flip this, you had to introduce it, and then it gets consumed. So it's an intermediate, exactly. Right. So it's an intermediate.
Is produced and consumed an appropriate terminology for that?
Yes, it is.
Sweet.
I will even prove it to you. The O atom is an intermediate because it is formed and then consumed during the course of the reaction. Had it been a catalyst, it would have been present both at the beginning and the end of the reaction instead. Finally, one that some will have some more problems with, and this take meaning from, please. Last question. Identify the slower step in the mechanism if the rate law of the reaction was determined. So they found this out. It's not your job to say yes or no. They're saying this is what it is. Justify your answer. Justify.
Justin's big into rap.
So, which one's the slower step? First, let's talk about that. What is the slower step? The rate determining step. What is the rate determining step? The step that represents or resembles the rate law, based on a term that we learned, is called molecularity. Molecules literally have to collide, and when they collide, that is the chemistry that is actually occurring. So if you had to say one step was the rate law, or the slowest step, which is the rate determining step, step 1 or step 2? Step 1, these are still here. These are still here. So it's this one. And why? Because it shows that there is only one reactant, or shows that N2O exists as a single reactant. Is slower because NO2 appears in step 1 as a single reactant, which is consistent with the given rate law. Just to finish this off, if red doesn't count. If it was squared like that, the rate law should have like either 2 of these, like that, or another one like that. Because then that's based on molecularity. Like there's 2 of them colliding. Oh, the rate law resembles that there's 2. That's why a lot of times there will be a question, just to follow this up, where it'll have a rate law and it'll say, explain why or why not you know that this occurred in a single step or not. And they have an actual equation. Well, if the rate law doesn't look, let's say step 2 was the equation you were given. And they say, this is the rate law here. And step 2 is the only one you see. Did this happen in one step? You'd say no, because the rate law doesn't reflect the equation, because there should be oxygen in that rate law as well. I'm out.